Hello students, welcome back to the Tantray physics classes. Today we are discussing one more challenging problem on magnetic field and the circular motion of the charge in the magnetic field. I have already discussed one challenging problem in this on this, and today I am discussing one more problem. So the problem is like this. Try to understand the problem first. This is the region of the magnetic field, and the magnetic field is outwards, shown by dots. These dots show the magnetic field outwards. And the width of the field is h. I mean, the field extends over a distance of h. Means field is not here, field is not here, field is somewhere here. Right? Now, you project a charge perpendicular to the magnetic field in the plane of the board. The field is like this and the magnetic field is like this. So you are projecting the charge perpendicular to the magnetic field. The field is like this out and the charge is projected like this. Now this charge, when the field is like this and charge is projected like this will become a circle. This will become a circle, and the circle is in such a sense that the magnetic field of the charge itself is inwards. Because it goes into the magnetic field which is outwards, it will send its own magnetic field inwards. It is something Newton's third law, to every action there is equal and opposite reaction. When the charge goes up, this magnetic field tends to curve it, and this charge will try to kill this field. So this charge creates its own magnetic field in the inward direction. So that gives you to understand why should the sense of the charge motion is like this. The sense of the charge motion is like this because the field is the charge creates its own magnetic field inwards because the magnetic field is outwards. This outward magnetic field, and the charge is projected like this, it becomes a curve and emerges out here. Because you see, the h is less than r. Here h is less than r. So that it will not complete a circle and come back. It will emerge out of the magnetic field. And not only that, the charge is perpendicular to magnetic field. Charge also normal or perpendicular to the boundary of the field. It is the boundary of the field. The charge also makes 90 with the boundary. It makes also 90 with the magnetic field, also with the boundary. Something like this. This is the boundary of the field, right? The charge is projected like this. This is boundary of the field. So field starts from here. So it is like the charge could have been like this, not perpendicular to the boundary, but still the charge would have been perpendicular to the magnetic field because magnetic field is outwards. I want to explain like this. This is a magnetic field. This is the projection of the charge. This is the magnetic field. The projection of the charge would have been like this. Still it would have been perpendicular to the magnetic field, but not perpendicular to the boundary. But now here, the magnetic field is perpendicular to the magnetic field, perpendicular to the magnetic field. It is also perpendicular to the boundary of the magnetic field. That's very important. Perpendicular to this line also. Okay. Now, the width of the field is h, the magnetic field is outwards, and this charge will become a circle or an arc of a circle or a part of the circle in the magnetic field. That I have already discussed in earlier problem, that when a charge is projected perpendicular to the magnetic field, it becomes a circle, whose radius is given by the equation that I have already given there, but here also I will repeat. The radius of the circle in which the charge moves in the magnetic field, I have derived it there, but here I am just going to write it down. The R is equal to momentum by QB. The radius of the circle, or radius of the part of the circle, or radius of the arc in which the charge moves in the magnetic field, is just mv by qb. We have already discussed that in the earlier problem. Okay. Now what is the question? The question is, what is the deviation of the charge caused by the magnetic field? Charge projection ऐसे था, अगर फील्ड नहीं होता तो सीधे चला जाता चार्ज, लेकिन फील्ड की वजह से ये चार्ज यूं चला जाता है. तो मुझे निकालना है कि, चलो इसको सॉलिड लाइन ही कर लो क्योंकि डॉट से ये कंफ्यूजन हो सकता है. तो ये थीटा है, ये थीटा हमें निकालना है. अगर ये थीटा मुझे निकालना है, हाउ मच द चार्ज हैज डिविएटेड फ्रॉम द वर्टिकल लाइन, तो इसका मतलब ये भी थीटा है, दिस मीन्स दिस इज ऑल्सो थीटा. अगर ये थीटा है तो दिस 90 बिकॉज दिस इज 90. अगर ये 90 है, ये थीटा है, दिस इज 90 माइनस थीटा. तो अगर ये 90 माइनस थीटा है तो दिस इज थीटा. या सीधे आप कर सकते हैं, अगर ये थीटा है तो ये भी थीटा है. दिस इज थीटा, दिस इज थीटा. अगर ये थीटा है तो ये भी थीटा है. सो वेरी ऑब्वियस, अगर ये थीटा, ये 90 माइनस थीटा हो गया, और ये ट्रायंगल का 90 माइनस थीटा 90 और ये थीटा होगा. तो फाइनली वी हैव टू फाइंड व्हाट इज this theta, and also what are the x and y components of the velocity when the charge comes out of the field. जब ये चार्ज फील्ड से बाहर आता है तो इस वेलोसिटी के x और y कंपोनेंट क्या है. तो मुझे निकालना है vx निकालना है और vy निकालना है. मुझे इसके दो कंपोनेंट्स मुझे निकालने हैं. First of all, I must tell you, yes, these two things I will find. First, I will find theta. Then, I will find the x and y components of this velocity that I will find. But before I do that, I must explain you certain things. Let me explain you certain things. Okay, let me rub it off because you already know what we have to find. What we have to find? We have to find this theta. When the charge goes into the magnetic field, how much deviation is caused by the magnetic field? And also, we have to find the x and y components of this velocity when the charge emerges out of the field. That's what we have to find. So you must keep that in your mind, what we need to find. Okay, let me rub it off so that I can write it here. Here I want to tell you one more thing, one important thing. When the charge having some velocity goes into the magnetic field, the magnetic field is such, as you know, F is equal to QV cross B. The magnetic field is perpendicular to velocity. The magnetic force is perpendicular to velocity, and it is also perpendicular to the magnetic field. That is the force, magnetic force, very typical force, unique property. Force is perpendicular to velocity and magnetic field. As such, when the force is perpendicular to velocity, it will not do any work on the charge. I mean, the kinetic energy of the charge will remain constant, or the speed of the charge will remain unchanged. It's a well-known fact. Magnetic fields don't do any work. There's my lecture on the YouTube. Magnetic fields do not do any work on the charges. So you can watch that lecture in your free time. Okay. Now, so that's why I have shown the charge enters with the speed v0 and also leaves with the speed v0, because the magnetic field has not worked on the charge. The kinetic energy of the charge remains constant. If the kinetic energy of the charge remains constant in the magnetic field, therefore its speed will also remain constant. So it enters with the speed v0, it leaves with the velocity speed v0. Of course, velocity changes because there is a deviation. Okay. So, okay. Can you tell me what is the, when you draw a perpendicular here, when the charge emerges out, you draw a perpendicular here on the arc here, and you draw a perpendicular on the arc here. These two normals on the arc here and here will meet at the center of the arc. It is as if there's a circle. Draw perpendicular here, it will meet at the center. Draw perpendicular here, it will meet at the center. Draw perpendicular here, it will meet at the center. So if you draw a perpendicular to the arc here and to the arc here, they will meet at the center. So this is the center of this arc, and therefore this is the radius of that arc, and this is also the radius of the arc. ये भी radius arc का radius है, ये भी arc का radius है, r. So what is that r equal to? What is that r equal to? Radius of this arc. Radius of the arc is, yes, that's mv0 by qb. Equation first. Where q is the charge of the particle, v0 is the velocity, the speed with which the charge enters, and m is the mass of the charge. M is the mass of the charge. This is the radius of the arc in which the charge moves in the given magnetic field. Okay, Now, in this triangle, we have to find finally theta. In this triangle, what is this theta? From here to here, it is h width, and therefore from here to here, it is h. So, what is sine theta? Sine theta is perpendicular, that's h by r. This r is from here to here. This r is from here to here. This r is from here to here. So it is sine theta, this perpendicular by hypotenuse. This one. This. Okay. Now what is sine theta? That is h. That is given. What is r? That is mv0 by qb. That will make it h qb by mv0. So sine theta is equal to h qb by mv0. What is theta? That we have to find deviation. Sine inverse, yes, h qb by mv0. That is the answer within 3 steps. You find sine theta from the triangle, then there's h by r. Sine theta is h by r is given to be this, that I have already obtained in the earlier lecture, and you put it here, and then qb goes up and mv0, and theta is given to be h qb mv0 sine inverse of. Substitute these values, get the theta. So half the question is done. So what I need to find now, Vx and Vy, these two components. So let me go to these components, but I should remember this and this at least. Sine theta is equal to h qb by mv0. Okay, let me remember this, or let me keep it here so that I may use it. If the need arises, I may be able to use it. Okay, now when the charge emerges out of the field, you know its speed is the same, that is v0. So what is Vy? Put this into components, this v0, it is v0 cos theta, it is v0 sin theta. Theta is defined with a vertical axis, that is why Vy is cos component, and this Vx is sin component, because theta is defined with a vertical line. So what is Vy? That is v0 cos of theta. And what is Vx? That is v0 sine of theta. This is sine component because the theta is given with the vertical axis. Now, okay, first let me find this, because this is easy to find, because sine theta I already know. Vx is equal to v0 sine theta substituted from here, h q b by m v0. This cancels off. This Vx is equal to h q b by m. Question easily done. This is the x component of the velocity when the charge emerges out of the field. This is the x component of the velocity which we have found. It is h q b by m. All the parameters on the right side are given because they are defined in the problem itself. Okay, now what about Vy? Vy is equal to v0. What's cos theta? That is root of 1 minus sine square theta. Right? Okay, now what's Vy? Vertical component of the emergent particle. What's that? v0 root of 1 minus, what is sine square theta? You have to square this one. It is h q b by m v0 square. Okay, let this be the answer. Finished. So you have Vx and you have Vy. So what we have done, if I summarize it like this, you project a charge perpendicular to the magnetic field, perpendicular to the boundary of the magnetic field, it becomes an arc. It will not complete a circle because h is less than r. Had the h been greater than r, then it will go up and curve and will come back, and will make a complete arc before coming back to the before emerging out of the field. So it would have emerged like this back. But now the H is less than or, therefore it will emerge out of the field. So what we need to do, when we summarize, the charge is projected in the magnetic field, perpendicular to the magnetic field and perpendicular to the boundary of the magnetic field. It becomes an arc. We have to find how much it will get deviated from the vertical axis. How much it will get deviated from the vertical axis theta that we have found by using 2 or 3 equations. And then we have also to find its x and y components when it emerges out of the field. That also we have done very easily, because you see Vy is equal to V0 cos theta and Vx is equal to V0 sin theta. We already know sin theta, and we can convert cos theta into sin theta. That's very simple, and we have done that. Now, very important in this question was, when you project a charge with the velocity V0, it will come out of the field with the same speed, because the magnetic force is not doing any work. The force will change the velocity, of course, but it will not change the speed. That's all. So again, I ask you, the students, to watch my lectures on YouTube and also download my app, Tantray Sir Physics Classes. There is a whole lot of literature questions, objectives in that app. You can download them. You can watch my lectures there, so that you could be benefited and finally you can get selected at any national level in physics. Okay, thank you.